Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last session, we discussed about the stress analysis of wing, and in which we solved problems, and even we have seen if the varying modulus of rigidity is given, then how the analysis will be done. Now let's try to take that, and in this present analysis, we're going to solve problems of stress analysis of wings. And the learning outcomes in this module are students are able to solve problems on wing sections that are subjected to booms. So to understand this, let's try to calculate, let's try to consider this one problem. And so this is again a wing cell, and in which a torque of 11,300 Newton meter is applied simultaneously on all the three cells. So he has given this is a cell 1, this is cell 2, and this is cell 3. So this is in fact he has given is 3-cell wing section that is given to us. So what he is asking to calculate? So he is asking to calculate the shear stress distribution in the walls of the 3-cell wing section shown in figure when it is subjected to an anti-clockwise torque of 11.3 kilonewton meter. So he has given an anti-clockwise torque of 11.3 kilonewton meter, and is asking to calculate the shear stress distribution. So shear stress distribution is asking to calculate. Okay, shear stress distribution tau. Okay, so if you want to calculate the shear stress distribution in all the walls, and what you can do here before that, so you can consider the shear flow distribution in all the walls, because we know that the relationship for Q and tau, that is a shear flow and shear stress, is nothing but Q equals to tau into T. So that once you get this shear flow, you can divide the shear flow by the respective wall thicknesses, and then you will get correspondingly the shear stresses in all the walls for the cells 1, 2 and 3. Okay, so this is the procedure. But this problem, when you look at this one, it is related to torsion. So when the torsion, when the torque is applied 11,300 Newton meter simultaneously on all the 3-cell wings, so that you have to take the formulae which we have discussed in the last session. That the first formula will consider torque, that is T equals to 2AQ, and the second formula that we consider is rate of twist, so that is equals to 1 by 2AG cyclic integral of Q ds by T. This is the rate of twist formula. But when you look at this given data, the modulus of rigidity is given different values for all the different walls. Okay, so that is a varying modulus of rigidity values are given. So when that has given, this rate of twist formula we have modified in the previous session, that you can write this as 1 by 2A into G reference into cyclic integral of, and this you can see here we have written this as ds by T star, and we've added here G by G reference into T, and this G by G reference into T we consider it as T star, that is nothing but the modulus weighted ratio. Okay, so this is how we'll try to use this formula, and in fact this completely now we'll write it as ds by T star, and that you can consider it as delta. Okay, right. So this is how we'll try to solve this problem. So slightly the procedure slightly differs for the last session problem which we have solved. So when you look at this problem, and he has given different wall lengths. So this is 1 to outer wall which is given here, and then this is the 1 to inner wall that you have to understand first, and this is walls 1, 3 and 2, 4, and wall 3, 4, and then 3, 5, 4, 6 which are the common walls, and here 1, 3, 2, 4 are the common walls. So that's he has given in the commonly. So he has given the lengths of these walls also. For example, 1 to outer wall is nothing but length is nothing but 1650 mm, this one, and then 1 to inner wall length is 508, 1, 3, 2, 4. So these are nothing but 775, and 3, 4 is again 380, and then he has given 3, 5 and 4, 6 as 508, and then 5, 6 as 254, and he has given the respective wall thicknesses also, and then he has given the cell areas, because it is uh, it is an arbitrary cells which is taken here, and he has directly given the cell area for 1, 2, 3 separately over here in this tabular, in this column. Okay, so this is all the given data. So, and let's go with our procedure. So since the wing section is loaded by the pure torque, the presence of booms has no effect on the analysis. So choosing G reference value, the very first thing what you have to do is choosing G reference value. So out of all these values which are given, 27,600 Newton per mm square is the highest value of modulus of rigidity, and it is given for walls 1 to inner wall as well as 3, 4 wall that is given. So let's take this two values or any one value as G reference value, and then we'll try to solve the analysis. And then now the T star of 1, 2. So what is the formula? T star, that is equals to G by G reference into T. Okay, and since we are considering first for 1, 2 outer wall, so you have to write G of outer wall and the reference value of G into T of 1, 2 naught. So when you try to do this, G12, that is modulus of rigidity for the 1, 2 outer wall. So for the 1, 2 outer wall, the modulus of rigidity is 24,200. So we are right here 24,200 divided by reference value, we consider it as 27,600 into its thickness. So its thickness, wall thickness is given by 1.22, and then we'll write it as 1.22. So we get T star, that is modulus weighted thickness for the outer wall. So T star outer wall, that is equals to 1.07 mm. Okay, which you got here. Okay, in the similar manner, you can calculate the modulus weighted thickness, that is T star, for all the different walls, so that you get T star 13, that is equals to T star 24 equals to 1.07 mm. T star 35, that is equals to T star 46, that is equals to T star 56, that is equals to 0.69 mm. Okay, so once you get this T star values, and you can substitute in the formula, because we know that cyclic integral of ds by T star is nothing but we assumed it as delta. Okay, so similarly, like how we calculated modulus weighted thickness for all the walls, that is 1 to naught, and then 1, 3, 2, 4, 3, 5, 4, 6 and 5, 6 like this. Similarly, we try to calculate delta for all the walls. Okay, so let's try to calculate first for the first wall, that is outer wall 1, 2. So delta 1, 2 naught, that is equals to cyclic integral of ds by T star of 1, 2 outer. Okay, so ds is nothing but this is a cyclic integral. Okay, so when this is a cyclic integral, ds is nothing but the wall length. For 1, 2 outer, what is the wall length that is given? For outer wall, 1, 2 outer wall, the wall length is given as 1650. So we substitute here 1650, that is a outer wall length, divided by T star 1, 2 naught. We calculated, we got it as 1.07. So that you'll get delta 1, 2 naught, that is equals to 1542. Okay. In the similar manner, we try to calculate the delta values for all the respective walls. So delta 1, 2 for the inner wall, you will get it as 250, and delta 1, 3, 2, 4, that you get it as 725, delta 3, 4 as 233, 3, 5 and 4, 6 as 736, delta 5, 6 as 368. Okay, so substituting the appropriate values of delta in the equation what we got in the previous equation. So this equation, whatever we get this equation, so we'll try to substitute in this equation, and then when you try to write for cell 1, and when you try to the rate of twist, so the rate of twist formula, that is equals to d theta by dz, that is equals to what you write, 1 divided by 2 into g. So g into area of first cell. So area of the first cell is nothing but 258000. So we write area and the G reference value. Okay, and then if you look at the shear flows, for cell 1, so there is one outer wall. Let's consider this as Q1 as the shear flow. So in this wall, Q1 is the shear flow, and when it comes to this wall, the shear flow would be Q1 minus Q2. Okay, because this is a common wall, so the shear flow, when you try to write the shear flow like this, so shear flow in this wall would be Q1, whereas in this wall, common wall, that is equals to Q1 minus Q2 is the shear flow, because Q1 shear flow acts like this, and when you try to consider Q2 shear flow will be acting in the downward direction, so Q1 acting in the upward direction. So we have to take the subtraction of this one, Q1 minus Q2 for cell 1. And similarly, so cyclic integral of Q ds by T will write, and what I am trying to write here, it is Q1 first, Q1 for the outer wall. So for the outer wall, what I got is, for the outer wall, delta 1 2 star directly write. So delta 1 2 star for the outer wall is 1542, and then next what you will write, for cell 1, you have two walls, that is 1 to outer as well as 1 to inner. So 1 to inner if you try to write, and that will be, how do we write? So Q1 into 1542 plus Q1 minus Q2 into the second for the inner wall, that is equals to 250. And if you try to split this equation, what do you get? Q1 into 1542 plus, again you can take this common, so you'll get 250, and then minus Q2 into 250. Okay, so this is the equation number 1 we consider. So this is the rate of twist for cell 1. Similarly, we'll try to write the rate of twist for cell 2. So when you try to write rate of twist for cell 2, 1 by 2 into area of the second cell, that is 355,000 into G reference. And then if you try to write for this one, so this is the common wall, and in which we'll consider this as Q2. So here the shear flow will be Q2, and here the shear flow will be Q1, and here the shear flow will be Q3. So that here the shear flow will be Q3 in this common wall, whereas the shear flow in this wall is Q2. Okay, so if you look at into this one, when you try to write, so first consider all these walls. So the common wall, so for 1 2, 2 4, 4 3 and 3 1. So this is cell 2. So therefore what you can write here, it is, first you can write the common walls. First, for example, the shear flow in this is nothing but Q2. The shear flow in this wall is nothing but Q2. Whereas the common walls for 1 2, 2, the shear flow would be Q2 minus Q1. Whereas the common wall 3 4, the shear flow would be Q2 minus Q3. That you have to consider. Okay, and if you try to write this equation, we'll try to write in the form, and this is directly given, so we have to write it in our own words. So first let's try to write the separate equation, that is 2 4. Let's try to write. So 2 4, that is equals to, the shear flow in this is Q2, and what we got, delta for 2 4 and 1 3. So 2 4 and 1 3, you got 725. Okay, so we'll write 725 plus 725, such that you will get for 2 4 as well as 1 3. And let's try to write next for wall 1 2. So for wall 1 2, the shear flow would be Q2 minus Q1 into its delta value. What we got is 250. So now let's write 250. Similarly, for wall 3 4, the shear flow would be Q2 minus Q3 into 3 4. What we got for 3 4? 3 4 delta is 233, and we'll write right here, it is 233. And then we'll try to write it in the own equation, that is separating all the shear flows. So first we got Q1 as minus 250, so we got minus 250 Q1. This is over. And then if you try to write Q2, so here you got Q2 into 725 plus 725, and again Q2 into 250, and then Q2 into 233. So we'll write all this. So when you try to write for Q2, so first 725 plus 725 plus 250 from here, and then 233. So I am writing the coefficients of all Q2. Okay. Next, what is left is Q3. So Q3 only present over here. So that straight away we can write. So that is Q3 into 233. Okay. So this is what equation number 2. So in the similar manner, we try to write the rate of twist in cell 3 also. So if you look at this cell 3, and we assume that the shear flow in this is Q3, and so therefore here the shear flow will be Q3, and here the shear flow is already there, that is Q2, whereas in this it is Q3, in this it is Q3, and in this wall also it is Q3. So first straight away you can write, so the rate of twist in third cell, that is 1 by 2 into area of the third cell is 161,000 into G reference, and then when you try to write this equation, and Q3 is the common for all the 3 walls, so therefore Q3 of 4 delta of 46, delta of 65 plus delta of 53, that you have to do. So delta of 46 and delta of 35, you get 736 each, and 56 is 368. So you will write 736 plus 736 plus 568, so that it will cover all the 3 walls. Now let's try to write for the common wall. So for the common wall, the shear flow would be Q3 minus Q2 cell, because the 3, 4 is the common wall for cell 3 as well as cell 2, into 3, 4. So for 3, 4, what we got for 3, 4 is 233. So we'll write 233. And if you try to write in the equation form, what you can do here, it is there is no Q1 values in this equation, and what we have is only Q2, and that Q2 also we got Q3 minus Q2 into 233. So only one value you got. So straight away we'll write minus 233 into Q2 first. Then when you take Q3 common, you get 736, 568. In fact, this is not 368. So you get 368 and then 233. So this is how we try to write the rate of twist equations for cells 1, 2 and 3. Okay. And do not forget that we have to write the torque equation also. So the torque equation for all the 3 cells, which is nothing but 2A1 Q1 plus 2A2 Q2 plus 2A3 Q3. Okay, and we'll try to write this form. So the torque is given as 11,600. So torque is given as 11,600 Newton meter, but you have to convert that into mm, so that you can write 11,600 into 10 to the power of 3 Newton mm. So the applied torque is 11.3. You can write in terms of 10 power 6, 11.3 into 10 to the power of 6, that is equals to 2AQ, 2A1 Q1 plus 2A2 Q2 plus 2A3 Q3. You can take 2 common, and area of cell 1 is 258,000 into Q1 plus area of cell 2 is 355,000 into Q2 plus area of cell 3 161,000 into Q3. So this is the fourth equation you can consider. Now what you can do here, it is you can solve all the simultaneous equations number 1, 2, 3, 4. Then you can get easily the shear flows Q1, Q2, Q3. Now for this problem, we got the shear flows that Q1, that is equals to 7.1 Newton per mm, and Q2 equals to 8.9 Newton per mm, and Q3 equals to 4.2 Newton per mm. So this is how we solve problems on shear to find out the shear flows for a wing section which is subjected to torsion. But in the question, he has given to calculate the shear stress distribution. Now what we got here is the shear flows Q12, Q23 and Q34. Now what you can do, you can calculate the shear stress distributions just like by using the formula for shear flow. And we have seen that the shear flow is equal to tau into T. So what we got? Tau. So tau equals to Q by T you can use. Okay. Now for the first cell, we got the shear flow as 7.1 Newton per mm. So now what you can do, if you want to calculate shear stress for the outer wall, then the shear flow in this wall is nothing but how much? 7.1, and divided by thickness of the outer wall you can use, which is nothing but 7.22. So you will get this, and you can write this in terms of Newton per mm square. Similarly, if you want to calculate shear stress in wall 1 to inner, then what you can do is shear flow, because in this wall the shear flow will be Q1 minus Q2. So Q1 minus Q2 is nothing but 7.1 minus 8.9 is the shear flow divided by its wall thickness. So 1 to inner wall thickness is given as 2.03. So you can write 2.03 and you will get the shear stress in inner wall. So like that you can calculate the shear stress in all the other walls, that is 2, 4, 3, 1, and you can calculate the shear stress in wall 3, 4, and you can calculate the shear stress in walls 4, 6 and 3, 5, and you can calculate the shear stress in the wall 5, 6 by just writing their respective wall shear flows divided by their actual thickness of the wall. Okay, so this is how we calculate the shear stress distribution for all the walls. Okay, so that's it for today's class. So in the next session, we'll try to solve more problems on the stress analysis subjected to wing, and then we'll try to see the cutouts in fuselage as well as wings. So thank you everyone for watching.